we'll now look at the ranges of a binary number. So what does that mean? So now let's say we take only one bit. So one bit can be either 0 or 1, right? So then if I have one bit, I can store only two values. Okay, and this can be also represented as 2 raised to 1. So 1 is the amount of bits, which is 1 bit, and 2 is since each possible combination, the number of combinations that we have for each bit is 0 and 1, which is 2. So that way 2 raised to 1, and so 2 raised to 1 is again 2. So 2 values is what we can store. So now let's take an example of 2 bits. Okay, so 2 bits, each bit can have either 0 or 1, right? So this can be either 0 or 1. Okay, similarly this position can be 0, and then again this position can be 0 or 1, right? So in total, how many combinations we have? We have total 4 values that we can accommodate. Okay, so again, if we take the same formula, so we have 2 raised to 2, because now here we have 2 bits, and that is what we'll raise 2 to the power. Okay, so here we'll write it as 4. So the generalization of this is, if you have n bits, you can store how many values? 2 to the power n values. So in case of 1, we have 2 raised to 1 value we can store. In case of 2, we have 2 raised to 2. So this is equal to 2, this is equal to 4. Similarly for 3, we have 2 raised to 3, which is equal to 8 values. So if you have to look at, if we have 3 bits, so what we'll have? So we have again 3 positions. So this can be either 0 or 1. Okay, and this can be 0, and this can be 0. Okay, now again we can have 0 or 1, and this can be 1, and this can be 0, and then this whole thing will be repeated with this all bits changed to 1, because we have now taken 0. Now we'll just take 1. So if I take the same thing, 1 1 1 1, so this way we got, this were the 4 combinations, this were the 4 combinations, so total we got 8 combinations or 8 values. And since we have 3 bits, so our formula was 2 raised to n, so which is equal to 2 raised to 3, which is equal to 8 values or possible combinations. Okay, so that is how we came up with this generalization. If we have n bits, you can store up to 2 raised to n values or combinations. Now, given these values, what is the range that we can store? Since my first number is always 0 and this last number is all ones, which is in this case is 7. So if my first value is 0 and last value is 7, and total if I can store only 8 values, so I can store up to 0 to, what is this, 2 raised to n minus 1, right? So my here n is equal to 3, so here n is equal to 3, so 2 raised to 3, which is 8, minus 1 is 7. So the maximum value is 7 and the minimum value always starts from 0. So in case you have an unsigned number of n bits, you can store from 0 to 2 raised to n minus 1. Okay, so this is what we have established now. We'll take a look at the signed numbers further. So what do we mean by first signed numbers? So signed numbers in decimal, let's say, can mean any positive values like +8, +100, or negative values, let's say -7, -23, and things like that. So this sign indicates whether it's a positive number or a negative number. Similarly, in binary, we can have positive as well as negative numbers. So how are first the binary numbers represent the negative numbers? So how do we represent negative numbers in binary format? So we'll first take a look at that. So before we take a look at that, we'll have to understand what is a 2's complement. Okay. So what do we mean by 2's complement? So 2's complement is a way to represent negative numbers in a computer or in binary format. So let's say if you want to store -6. Okay. So ignore this negative sign for now. So first we'll take a look at how would we store 6 in a 4-bit number first. Okay. Assume that we have at max 4 bits to store the 6. Okay. So why 4 bits? We'll come to it later. So now 6 can be represented as what? 1 1 0, right? So this is 4 and this is 2, because this is 0th position, this is first position, this is second position. So this will be 1 into 2 raised to 2 plus 1 into 2 raised to 1 plus 0 into 2 raised to 0. So this will be equal to 4 plus 2 plus 0, which will be 6. Okay. So 6 would be represented in such a way. Okay. So 6 is represented as 110. Since we are taking 4 bits, the 0th or the most significant bit would be represented as 0. Okay. But now we want to store -6, right? And this number represents +6, but not -6. So how do we convert this to -6? So this is the question. So for that, we do something called as 2's complement. So what does 2's complement mean? So 2's complement is actually 1's complement plus 1. Now what is 1's complement? 1's complement is nothing but invert all the bits. Invert all the bits. Invert, or I would say reverse all the bits, and then add 1 to that reversed or inverted number. So here what we'll do, we'll first take 1's complement. So what that would mean, zeros would change to 1 and 1 would change to zeros. So this first 0 will change to 1, 1 will change to 0, 1 will change to 0, and 0 will change to 1. Okay, this is 1's complement. And then we'll add 1 plus 1. So now we'll do a binary addition. So 1 and 1 is what? 2. But 2 in binary is represented as what? 1 and 0. So we'll write 0 here and carry 1 here at the top. Again, so there is nothing here. So this is all zeros actually. So 0, 0, 0 and 0 is 0, and this carry 1. So this will be 1. Okay, no carry from this. So 0 plus 0 will be 0, 1 and 0 will be 1. Okay, so this number actually represents what? So this number represents -6 in binary. So this is how negative numbers are typically represented in a computer system. So now we'll continue with the same example. Let's say we had only 3 bits. So in 3 bits, our combinations were all of these numbers, right? So these were all the possible combinations that I had. So we'll take this same and we'll see. So here were our 3-bit numbers. So in 3 bits, our unsigned range was what? 0 to 7. Okay. But now what we'll do, we'll try to convert each number in a positive and negative number, and we'll see what is our range. So this is 0, this is 1, this is 2, and this is 3. Okay, and since this is only a 3-bit number, and as we saw earlier here, so here what did we see? If my number is negative, right, the most significant bit or the leftmost bit is set to 1. Okay, so that is true in any case. So here, since all these bits here are set to 1, so all this represent actually the negative numbers. Okay, so now what we'll do to convert these numbers to positive numbers, we'll do the reverse mapping. So let's do that for 1 0 0. So the ones complement of this is will be what? 0 1 1, and if I do add 1, so this will be plus 1. Addition of 1 and 1 will be 0, added 1, 1 and 1 would be 0, carry 1, and 0 0 and 1 would be 1. So we get the same number. Okay, so this in decimal is what? 0 1 and 2. So this is 2 power 2. So this whole number is actually equal to 4. Rest all are zeros. Okay, so this is how we'll do for the other numbers as well. So this number is actually 4, but since the most significant bit is 1 here, so this represents -4. Okay, now similarly, let's look at this number 101. So we'll again do the same thing. 101 will take 1's complement, so it will be 0 1 and 0, and we'll do plus 1. So 1, add 1, 1 and 0 is 1, 1 and 0 is 1, 0 and 0 is 0. So this is what? 1 1. 1 1 means this is 2 power 1, this is 2 power 0, which is 2 plus 1 means 3. So this number is actually -3. Why -3 again? Because the most significant bit is 1, so that's why we added minus sign, and the magnitude of that number is represented by the 2's complement that we took. So that was 3, so that's why we wrote here 3. Okay, similarly we'll do for this and see what does that give us. Okay, so again 1 1 0, we do 1's complement, it will be what? 0 0 1, we do plus 1, so add 1, 1 and 1 is 0, carry 1, so 1 and all zeros is 1, carry, so 0 1 0. So this is actually 2 raised to 1, and so which will be equal to 2. So this is actually -2. Okay, and again same if we do for 1 1 1. Okay, we invert everything, so 1's complement, so we do 0 0 0, inverted everything, plus 1 will be 1 and 0 0. Okay, so the last number here actually represents -1, because this is only 1 here, so it is actually 1, and since the most significant bit is 1 here, so that's why this is the minus sign. Okay, so now with all this, where did we land? So our least value is what? -4, and our maximum value is what? +3, right, for a 3-bit number. Okay, so if I had n-bit number, so what would be our range? So -4 can be also represented as what? 2 raised to 2, -2 raised to 2, and -2 raised to 2 I can represent it as what? -2 raised to 3 minus 1. Why 3? Because we have a 3-bit number, and 3's are actually the number of bits. So we are trying to represent this -4 by considering 3 as my input number of bits. Okay, and the +3, how can I represent it as? So I'll take here, so +3 I can write it as what? I can write it as 4 minus 1, right, and 4 is what? 2 raised to 2 minus 1. So this is actually 2 raised to 3 minus 1 minus 1. Why 3 again? Because 3 is the number of input bits. So for any given n bit number, my range becomes minus 2 raised to n minus 1 to plus 2 raised to n minus 1 minus 1. Okay. Let's say our number was 8 bit number. So we'll write now unsigned and signed ranges. So for unsigned, what was our equation that we came up earlier? It was 0 to 2 raised to n minus 1. Okay, so for unsigned 8 bit, we will have 0 to 2 raised to 8 minus 1, which is 0 to 2 raised to 8 is 256 minus 1, so 0 to 255. So for an 8 bit unsigned number, we can store 0 to 255. So similarly for signed, what did we come up with? Minus 2 raised to n minus 1. Here 2 plus 2 raised to n minus 1 minus 1. Minus 2 raised to 8 minus 1 to 2 raised to 8 minus 1 minus 1. So this becomes 2 raised to 8 is again 256. And so this will be minus 2 raised to 8 minus 1 is 7. 2 raised to 8 minus 1 is 7 minus 1. Again 2 raised to 7 would be half of 2 raised to 8, which is 128. So this will be minus 128 to plus 128 minus 1, which will be 127. Okay. So this is what would the ranges be in case of an 8 bit unsigned and signed integers. So in this table now we'll look at the ranges for different sizes of integers. So we have taken 8 bit, 16 bit, 32 bit and 64 bit sizes integers. So 8 bit is typically 1 byte. So this 8 bit represents 1 byte integer. Similarly for 16 bit, it means 2 bytes. So this is a 2 byte integer. 32 bit is 4 bytes and 64 bit is 8 bytes, right? So we'll see the various ranges for both unsigned and signed integers for all these integer sizes. So as we established earlier, for an unsigned integer, the range is from 0 to 2 raised to n minus 1, right? So for an 8 bit or 1 byte integer, the range would be what? 0 to 2 raised to 8 minus 1, right? So this would be the range. Similarly for 16 bit, it would be what? 0 to, our n is 16, so 2 raised to 16 minus 1. Similarly for 32 bit, 0 to 2 raised to 32 minus 1, and 64 bit, it would be 0 to 2 raised to 64 minus 1. So whatever values of 2 raised to 8, 16, 32 and 64, if you substitute that, you would get the ranges. Like typically 2 raised to 8 is 256, so 0 to 2 raised to 8 minus 1 would be 256 minus 1, which means 255. Okay, and that is why the unsigned characters are from range 0 to 255. Okay, now coming to the signed ranges. So for signed, again the value of n, we have all these values of n, we'll just substitute it and we'll see. So for an 8 bit signed integer, what will be the range? Minus 2 raised to 8 minus 1 to plus 2 raised to 8 minus 1 minus 1. So this will be minus 2 raised to 7 to plus 2 raised to 8 minus 1 is 7 minus 1. So what does this mean? So this means minus 2 raised to 7 is what? 128, right? So if I just substitute that value, so it would be minus 128 to plus 127. 2 raised to 8 is 2 raised to 8 minus 1 is 2 raised to 7. So 2 raised to 7 is 128. 128 minus this one here is 127. So that is how we got the range for a 8-bit or 1 byte integer, for a signed integer. So this would be the range. Now similarly for 16 bits, if we look, so it would be what? Minus 2 raised to 16 minus 1, 2 plus 2 raised to 16 minus 1 minus 1. That turns out to be minus 2 raised to 15, 2 plus 2 raised to 15 minus 1. Okay, so this would be the range for a 16-bit or 2-byte integer. And above we saw was the range for what? 8-bit or 1-byte integer. Similarly for 32 bits, it would be what? Minus 2 raised to 32 minus 1, 2 plus 2 raised to 32 minus 1 minus 1. So this means minus 2 raised to 31, 2 plus 2 raised to 32 minus 1 is 31 minus 1. So again this would be the range for what? A 4 bytes integer. Okay, and similarly if we do the math for 64-bit integer, what would be the value? So it would be minus 2 raised to 64 minus 1, 2 plus 2 raised to 64 minus 1 minus 1. So this is minus 2 raised to 63, 2 plus 2 raised to 63 minus 1. So this is how we get the ranges for various sizes of integers.